Hello everyone. Today we're going to talk about earth fault loop impedance testing, which is a bit of a mouthful. Fortunately, the test itself is not as difficult as just saying that name. Firstly, then, let's just talk very briefly about what that test is and why do I want to do it. So earth fault loop impedance. What is the earth fault loop impedance? So imagine that when you turn on an appliance, you turn the power switch on, there's electricity coming to you from a transformer somewhere, a distribution transformer somewhere out in the neighborhood. The earth fault path will be the pathway that electricity takes to get from that transformer down the street, either under the ground or through overhead lines, to the mains connection at the front of the property, under the ground again, to down the driveway to our switchboard, through our main switch, through our circuit breaker, down that sub-circuit wire to the socket that you are connected to. And then, of course, it travels back again along the neutral. Now, if I were to have a fault on that circuit, a short circuit, a very high current will flow, or a very high current should flow, and then that trips the circuit breaker, right? That's how our primary protection by circuit breakers works. We have a short circuit, a high current flows, circuit breaker trips. However, if we do not test, we don't know how much that current is. And we really do want to know what that is. We need to know how much current will flow in that circuit in the event of a fault, so we can be sure that our circuit breakers will indeed operate, because it's a critical safety device for people. And if we're not certain that the circuit breaker will operate, then we're not sure that our installation is safe. So what do we need to know? Well, what we need to know is, if there was a short circuit, what is the resistance of that loop from the transformer down the road to my switchboard, to my sub-circuit, to my appliance, through the short circuit, back along the earth wire to my switchboard, and back to the transformer again. I want to know what that resistance is. That will allow me to work out how much current is going to flow in that short circuit, and then I can be sure, is enough current going to flow? Let's have a look at what the standard has to say about that. So we will go to ASNZS 3000 as we normally do, and we are in section 8 because section 8 contains all about testing. And I've already gone here to section 8.3.9, verification of impedance, earth fault loop impedance. Now, it says a lot of stuff here that essentially is the same as what I've just described, so we're not going to go through that. Let's just have a look at the results. It says that the values obtained shall satisfy the requirements of 5.7.4. That talks about how fast the circuit breaker device needs to trip. The requirement is deemed satisfied if, where supply is available, the earth fault loop impedance measured at the socket outlet does not exceed the value shown in table 8.1. Fantastic. So we need to go to table 8.1 to have a look at that. There is a clause A here talks about an alternative test that we can do, and you're more than welcome to read up on that one yourself, but we're just going to cover today doing the simplest test, which is earth fault loop impedance test with the earth fault loop impedance tester. This test here talks about measuring the resistance of individual conductors. So let's just have a quick look then at table 8.1, and here we have it here. So we've got down the left-hand side protective device rating, and at the top circuit breakers, type B, C, D, and fuses. Generally, for most of the work we will be doing, we're going to have type C circuit breakers. And if we're measuring a circuit with sockets on it, it's most likely to be 20. And in fact, the one we're going to look at today as a demonstration will be a 20 amp type C circuit breaker. So that tells me the maximum value for my earth fault loop impedance is 1.53 amps. 1.53 ohms. It's a resistance reading. All right, so before we have a look at the demo, let me just show you what we mean by our earth fault path. And here we have a picture of our distribution transformer. We've got our switchboard here with our neutral and earth bar, our circuit breaker and main switch. We have our socket, which is in the installation, and here's my earth loop impedance tester, which we will see in a moment. And so what this earth loop impedance tester does is puts a small current between phase and earth. And we see current traveling down the phase through my tester, back along the earth conductor to the earth busbar. At this point, it branches off two ways. The main current is going to go through my neutral and earth link, through the neutral bar, back along the main supply neutral, that's what MSN stands for, and back to my transformer. There'll be an alternative path here that will go through the earth, main earth conductor, down to my earth stake, through the ground to another earth stake, buried at the transformer, and back up to my transformer neutral point there. And then, of course, we complete the circuit by going out of the transformer, down the main supply conductor to our installation, through our main switch, through our fuse or circuit breaker, to my socket, and back to my tester. So that is the circuit that we will be testing. And what we're doing then is confirming the resistance of this entire path to ensure that it is low enough to make sure that my circuit protection device operates. Okay, so we have here then our earth fault loop impedance tester. In fact, this is a multifunction tester that does a number of things. We're not going to worry about the other ones today. It does voltage and continuity or resistance like most of our testers do. This one will also insulation resistance testing, which is covered in another video. And it does RCD testing, which is covered in another video. In fact, it does phase rotation as well, which we don't need to worry about. This meter will do just about every test that we need to do, which is very handy. And I've got 3 leads connected in the back here. You can see those are red, green, and blue. So that's phase, neutral, and earth. And they connect through to a normal plug. So I can plug this into any standard socket and do my testing that way, which is very handy. And for today, we're going to be connecting to this extension lead. Just a point to note, normally I would plug this straight into a socket at the wall. I don't have one within close enough reach in my workshop here, so I've just got an extension lead. That will add some resistance to my earth fault loop impedance path. As you can imagine, now my current has to come all the way down the phase conductor of this extension lead and back along the earth conductor before it gets to my socket. So I'm adding a significant amount of resistance, maybe an ohm or two, maybe an ohm, to my earth fault loop impedance path, which may mean that the test fails. But that's okay. If the test fails, we'll still achieve the result that we're looking for the purpose of this video, which is to demonstrate the test and have a look at the test results. So I'm going to turn this on. I've already selected here loop. Let me get that a bit closer. Loop, and it says there no trip. I've got a second one here that says loop high current. The difference between those, if you have a socket that's protected by an RCD, the high current setting will probably trip that RCD. The no trip setting will not. The circuit that we're testing today is protected by an RCD, so I'm going to use the no trip option for that one. And that's all I need to do, really. The next thing I need to do is push the button, and the magic test machine does the job for me. So I've got test button on the left-hand side here. You may have a meter that looks different to this, but it should have more or less the same functions. It'll have a loop function if you're doing loop testing, and it'll have a test button. And there we go. Push the test button, and we'll see what happens. So it's currently running a small current through that entire loop. It'll measure what that current is, and then that will be able, the machine will then be able to work out what the resistance is. And we can see there it's come up with 1.85 ohms. And helpfully, it's already done the maths for us, and so it will tell us what the current is, 127 amps. So what that's saying is, if we have a short circuit on this circuit connected to my extension lead, the total resistance or impedance that short circuit will encounter is 1.85 ohms, and the total current that will flow in that circuit will be 127 amps. If you do the maths here, Ohm's law, voltage divided by resistance, you should find 230 divided by 1.85 will equal roughly 1.27 127 amps. It might be a little bit different depending on what the actual supply voltage is here. I think it's a little bit over 230 volts, but nevertheless, the math should hold up fairly closely. Okay, so that's it. That's the test done. 1.85 ohms, 127 amps. All we need to do now is have a look at whether that is a acceptable result or not. So on our table, as I said, this circuit, you can't see it, but I've already confirmed it myself. This circuit is protected by a Type C circuit breaker, and it's a 20 amp circuit breaker. So my maximum value for my earth fault loop impedance is 1.53 ohms. In fact, if we just have a quick look back at our tester again, we'll see it's 1.85. So that means this is a failed test. I need my result to be less than 1.53, and in fact, I've got 1.85. So, failed test. That's okay for the purpose of what we're doing today, as I said. I suspect that is most likely due to the introduction of an extension lead into our testing circuit, which is going to increase our resistance. If I were to plug the tester straight into the socket, I suspect I would get a better result. Nevertheless, that is how we do an earth fault loop impedance test. Table 8.2, table 8.1 of ASNZS 3000 tells us what that maximum value is. So we just refer to that depending on what circuit breaker is protecting the circuit. And we compare that value, and there it is. That's all we need to do. So that covers it for today. Thank you very much for tuning in.